So this is just a quick review of your final exam. So my first question here has to do with order of operations. Let me get rid of that. That's not even the right answer. So the question here, order of operations, that means we have to do our PEMDAS. We're going to deal with our parentheses first. These ones don't do anything, so we're dealing with these ones. So we have 6 squared plus 93 times negative 76. Like I said, this one doesn't really do anything. It's just telling me I have a negative here. These ones I have to worry about. So according to PEMDAS, if I go inside my parentheses, I have to do multiplication and division first. So this is going to be 13, and 7 times 9 is going to be 63. So the next part is I'm going to go back in those parentheses, and now I can do that addition. And it's going to give me 76. Now I can do the exponent because I did parentheses. Now I'm on exponents. So 6 squared is just 36. Then what we're going to have is we have multiplication division left to right. So we just have the one that we have to worry about. Got my inequality. So let me find this again. So 93 times negative 76 is a negative 7,068. Then we do addition subtraction, whatever comes first, left to right. So we'd have to do the 36 minus the 7,068, which gives me a negative 7,032. And now I have to add the negative 7 or subtract the negative 7,032 minus 76. And that is going to give me negative 7,008. Here we want to evaluate this following expression. So we have 3c divided by 2b, and we know that b is 4 and c is 6. So this is 3 times 6, and then we're dividing by 2 times 4. So remember, order of operations, we do multiplication and division, whichever comes first, going left to right. So going left to right is this. So we get the 3 times 6. So I get my 18. Then going left to right, we get the division. So the 18 divided by 2, that gives me 9. And then I'm just left with these two, so I get 36. So this has to do with our rules of exponents. So one of our rules of exponents says that if we have two things multiplied together and we raise it to a power, we can distribute that power. So we have 4x to the 8, y to the 8, and all this is the power of 2. So that means this is really 4 to the power of 2 times x to the 8 to the power of 2 times y to the 8 to the power of 2. So this is just going to be 16. So the other rule we had was that if we had a number raised to a power, and then we raised that to a power again, we multiply those powers. So we got x raised to the 8 raised to the 2. That's going to be 8 times 2 is 16. Same thing here, y to the 16. So here we're going to solve. So we have 6x equals 7, sorry, 6x plus 7 equals 17 minus 5x plus x. For your first step, every time you're trying to solve a linear equation, is simplify both sides. So 6x plus 7 can't be simplified any further, but over here, I have like terms. I have the negative 5x and a positive x. This is really 17 minus 4x. Then I want to make sure everything with the x goes to one side and everything without an x goes to the other side. So I'm going to add the 4x. So it's away from this side, and it just gives us 17. 6x plus 4x is just 10x. And we still have that 7. And now I will subtract the 7. I have 10x equals 10. If I divide by 10, I'm going to be left with x is just equal to 1. So my solution is x is just 1. Correct. So my equation is x squared minus 4x minus 7. We just want to figure out what our function values are going to be. Oops. So if x is 0, I'm going to have 0 squared minus 4 times 0 minus 7, which leaves me with minus 7. Which is that point right there. If I have 1, I have 1 squared minus 4 times 1 minus 7. So that's just 1 minus 4 minus 7. So that is going to be a negative, let me see, 11, negative 12. Oh, sorry, that's a plus 1. So go back and do that one more time. Not a negative 12, it's a 1 minus a negative 11. So this is a negative 10. I just realized my point was in the wrong spot here. 0, negative 7, 1, negative 10. All right, so if we look at 2, we have 2 squared minus 4 times 2 minus 7. So we have 4 minus 8 minus 7. So it is 4 minus 15. So this is just negative 11. So 2, negative 11. Then 3, we have 3 squared minus 4 times 3 minus 7. So that is 9 minus 12 minus 7. And that is going to be a, here, let me double check that one. 9 minus 12 minus 7. It's a negative 10 again. And then my last one is 4. So 4 squared minus 4 times 4 minus 7. That is going to be 16 minus 8 minus 7. Look, one of my numbers is off here. Oh, minus 8. No, not minus 8, minus 16. There, that's why I'm off. So 16 minus 16 minus 4 should leave me with minus 7. And so we got our points and we can graph our line. Okay, this is adding or combination of functions. So we have f of x is x squared minus 4, g of x is 19 minus x. And we want to figure out what f minus g of negative 4 is. This is the same as saying, I want to know what f of minus 4 minus g of negative 4 is. So I just need to figure out what f of negative 4 is. So we see that should be a negative 4 squared. Remember, squaring that negative because we're replacing x with the negative 4 minus 4. So 16 minus 4 is going to give me 12. G to the negative 4 is going to be 19 minus a negative 4. So 19 plus 4, this is going to be 23. So if I just want to do the subtraction here, we know that g of negative 4 is 12. Or sorry, f of negative 4 is 12, g of negative 4 is 23. So 12 minus 23 leaves me minus 11. Problem there for a second. Here we want to find the slope of a line containing the following pairs of points. So if we just want slope, remember these points are x1, y1, x2, y2, and slope is just my y2 minus y1 over x2 minus x1. So we said y2 is -6. So -6 minus my y1, which is -4. So minus the -4. Then my x's, my x1 is, or x2 is 1, my x1 is 6. So this is -6 plus 4 over -5. Or you can say -2 over -5 or 2 over 5. So my slope is just m is 2 over 5. So using intercepts to graph, that means I need to find my x-intercept and I need to find my y-intercept. So x-intercepts happen when your y was 0 and y-intercepts happen when x is 0. So if I want y-intercepts, all I had to do was take this equation and just replace, for my x-intercept, sorry, I just had to take the equation and replace my y with a 0. So I'm left with 2x equals 6, which means that x would have to be 3. So I have an ordered pair where x is 3 and y is 0. That'd be about here. The scaling on this is a little off. That's counting by halves, or not halves, twos. Here I make x 0, so 2 times 0 minus 3y equals 6. Leaves me with a -3y and a 6. If I solve for y is just -2. So this is an ordered pair of x is 0 and y is -2. There you have it. There would be my line. So we want to find the equation of a line given these pair of points. So this requires us to find two things. We need slope. And we needed this equation, which was our point slope form. So it's y minus y1 equals mx minus x1. So I need to find that slope to put it in this equation. So first, let's label these points. I'm going to have these be my 1s, these be my 2s. So we have 6 minus 1 divided by 9 minus 3. This is going to be 5 over 6. Then over here, we already picked what our x1 and y1 are. We have y minus y1, which is 1. My slope is 5 over 6. Then we have x minus x1, which we said is 3. So y minus 1, this is going to be 5, 6x minus 15. That is going to be -5 over 2. So we add the 1. And y will just be 5, 6x minus, we add 1 to -3 over 2. So polynomials, adding, subtracting, all we were doing is really combining like terms. So if we have 2a minus 9, and then I'm subtracting the polynomial -7a plus 4. Remember, we got this negative here outside the parentheses that needs to distribute. So this is just 2a minus 9 plus 7a minus 4. Now we combine like terms. So we got 2a and a 7a. That gives me 9a. I got a -9 and a -4, -13. Now multiplying, this is where we did the FOIL. So I go c times c is c squared, c times -3, which is -3c, 5 times c, which is 5c, and 5 times -3, which is -15. And I just want to go back and simplify by combining like terms. So -3z plus 3c plus 5c is just 2c. So we get c squared plus 2c minus 15. Now factoring, the first thing you always want to do when you want to factor is see if we have a common factor of some sort. So what we'd see here is that everything we have here is divisible by 4. So I can factor out a 4 and I'm just left with y squared minus 14y plus 49. Now what I need is I need factors of 49 that I know should sum. Sorry, let me go back and fix that. Factors of 49 that should sum to my middle number of -14. So the only thing I'm trying to do is just factor this part in here. So two numbers that would work would be -7 times -7. They multiply to give me 49. And you could add them to get a -14. So my 4x squared minus 14y is 49. So this part in here can factor into y minus 7 and y minus 7. So you could leave it like this, or write 4y minus 7 squared. So this one, we can't factor out anything that's common because everything's not divisible by 3. The only thing I could, and there's not all divisible by s. So in this case, because I have the 3 out front, I'm going to have to use AC method. So in the previous question, I was able to pull out that 4, and then I was just left with a y squared with a coefficient of 1. That's when I can use reverse FOIL. This one has to be AC method because I can't get rid of the 3. AC method means I multiply A and C, which would be the 3, because remember A, B, C. So it would be the 3 and the 8. So I need factors of 24, because 3 times 8 is 24, and I need them to sum to give me that middle term of 10. So it's kind of like we did with reverse FOIL. There's just a slight difference here. So oh yeah, going through the numbers at work. 6 times 4 multiplied to give me 24. 6 plus 4 would give me 10. So we use this to split the 10. So we had 3s squared plus 10s plus 8. So those two numbers that we got are going to help me split 10s into 6s plus 4s plus 8. So here we did factoring by groups. So we just paired 2 points, two pairs of terms together. So here, if I have 6s squared plus, or 5s squared plus 6s, we can factor out a 3 and an s. So that just leave behind an s and a 2. We have 4s and 8, so I can factor out these two is just a 4, which leaves me with s plus 2. Now I can factor out an s plus 2. This is very clearly an s and not a 5. And I have 3s left over here plus 4. So this would be my factored form. So these were our complex numbers because we have a negative inside the square root. So we'd have to rewrite these as a square root of -1 times 16 and a square root of -1 times 4. So remember, we had a rule that said if we had two numbers under the same square root, we could break up the square root if they're multiplied. Two numbers multiplied together under square root, we can break up the square root. So this just turns into square root of -1 times square root of 16 times square root of -1 times square root of 4. And then we said that the square root of -1 is what we use to make that imaginary unit I. So this is just I. Square root of 16 is just 4. This is another I, and square root of 4 is just 2. So we have 4 times 2 times I times I, 8i squared. So if we had an I and we squared it, part of our complex number says that should be -1. So this is just 8 times -1. Sorry, I got that right. 8 times -1, which is going to be -8. I said something a little off there. Here we are solving. So you can use quadratic formula or you can use factoring. I'm going to just do this one with factoring. So if I did factoring, I would need two numbers. They're factors of 24, and I want to see if they sum to -5. So I know -8 times 3. There we go. -8 times 3 should be working because those multiplied gives me -24. -8 plus 3 would give me a -5. So I can rewrite this as v squared minus 5v minus 24 equals 0. And now it's going to be v minus 8, v plus 3. So I just did a reverse FOIL. So that means we have two choices here. V minus 8 is equal to 0, or v plus 3 is equal to 0. And if I solve them for the variable, we get v is equal to 8, or in this case, v plus 3 equals 0. We subtract 3 from both sides, and that is v is equal to -3. These are my two solutions that I can have. These are the two numbers that, if I replace them with v, would actually make the whole polynomial equal to 0. So these ones, so this is the case where there is no x term. We just have an x squared and we have the constant. In this case, we're going to solve for x by first solving for x squared. So we're going to have 3x squared minus 39 equals 0. First thing I'm going to do, I'm going to add 39 to both sides. Now I have 3x squared equals 39. Then I want that x squared by itself. I'm going to divide by 3, which is going to leave me with x squared is equal to 13. So if I have something squared equal to a number, that gives me two solutions. X is either going to be negative square root of 13, or x is going to be the positive square root of 13. And square root of 13 we can't simplify, so we leave it square root of 13. Okay. So if we want to solve, remember we always have to solve our equations so they're equal to 0. So if I did that, I have 3x squared plus 7 equals 5x. So I'm going to subtract 5x from both sides. So one side of this is equal to 0, and we're going to have 3x squared minus 5x plus 7 equals 0. So I set it up so it looks like ax squared plus bx plus c. So we keep our terms in order of power. So here I can use quadratic formula to solve. The quadratic formula is f is equal to negative b plus or minus the square root of b squared minus 4ac divided by 2a. So when we have this lined up over here, our a is going to be 3, our b is going to be negative 5, and our c is going to be 7. We just fill it in here. So we have a negative b, because originally it's negative here, but our b is negative 5. So negative 5 plus or minus the square root. So remember, it's that b is being replaced. We keep that negative 5 in parentheses, negative 5 squared minus 4 times a, which we said is 3, and c, which we said is 7. And this is all over 2a, so a was 3. So this is going to simplify to 5 plus or minus 25. And then, let me see, 4 times 3 times 7 is going to be 84. So this is going to be minus 84 over 6. So we got 5 plus or minus 25 minus 84, which is going to be minus 59 over 6. So remember that you can't do a square root of a negative number, so I do have to rewrite this. So that's 5 plus or minus, we can say I square root of 59. So we can just pull that I out, that negative as an I over 6. And that would be my solution. So this one has a complex solution. Okay, so identify minimums and maximums and the intervals in which the function is increasing, decreasing, or constant. We'll make it for the whole problem so we see all our questions. Okay. So if we want the relative maximum, that would be this point here because this is the highest in its area. So the relative maximum is always going to be the y component, would be that -1, and it's going to be located at the x value of -3. This one here is my minimum. The relative minimum, so the minimum itself, once again, is the y value, would be the -19, and the location is the x value at +3. Like I said, what we consider the relative minimum or maximum, that is a y value. Now, where is this increasing? And where is it decreasing? We don't have any constant to worry about here. So here are my boundaries. So from here to here, I'm increasing. And from here to here, I'm increasing. So it's going to just be x values, and we keep the intervals open. So starting at x from negative infinity, we are increasing right up till we get to x is equal to -3. At which point, that's when we start decreasing, which we see through here. So we're decreasing when x is -3, and we keep decreasing until we hit x is +3. At which point, we switch again, and now we're going up. So the other part where I'm increasing is going to be starting at +3, and then we keep going, our y values keep on going for infinity because this just keeps going and going. All right. Here we want to find the zeros of the polynomial and state the multiplicity of each. Remember, multiplicity was the power. So we have fx is equal to x to the fourth, x minus 2 squared, and we have x plus 8. So the x plus 8 has an invisible power of 1 on it. So as far as zeros go, we set this equal to 0, and we were trying to solve for zeros. Here, this is where x would have to be equal to 0, which is just x equals 0. And that power is 4, so we have multiplicity of 4. Here, if we went to 0, there's a possibility that x minus 2 would have to be equal to 0, which means then x would have to be equal to 2. So that is the actual 0. And my multiplicity here is also 2. In this case, we have 8 plus x is equal to 0, because we're trying to figure out where our zeros are, which if I solve this would end up being x is just equal to -8. And we have that invisible 1 on it. My multiplicity is 1. That's why my smallest zero is -8 with a multiplicity 1. My middle is 0 with a multiplicity 4. And the largest zero I have is 2 with a multiplicity of 2. So here we just want to sketch a graph of our polynomial. We have negative x squared minus 2x cubed. So things we want to know is first want to know where this is going to be equal to 0. So if I factor this, I could factor this into a negative x cubed, and then I just have x minus 2, which means my two zeros are either in x is equal to 0 out here, or an x minus 2 is equal to 0. So the zeros I have for this polynomial are going to be at 0 and at +2. That's one thing you need to consider. The other is what is the long-term behavior. So we need to do our leading term test. So leading term test, that is going to say, looking at that leading term, we have a negative x to the fourth. So by leading term test, what that means is that this has an even power, so we have a parabola of some sort. And then because it's a negative coefficient out front, it's just going to be this. So we know that end behavior is this. So going through here, we know we have something that has to have these zeros and this end behavior. So in this case, we can just eliminate onto end behavior and we see that this is the graph that would have to fit. So it has that same end behavior and you see that it looks like it crosses here at 0. Make that bigger. Like I said, and you see it crosses. They have this one graphed wrong. Oh no, because plus, -2. No, that's right. So it's been 0, -2. So it would have been crossing here at 0 and -2. That was my fault there for not distributing, for not pulling out my negatives. All right, so this is part of the newer material. So we want to do synthetic division and find the quotient and the remainder. So by synthetic division, what I want to keep here are just my coefficients. And then I need to make sure I'm not missing a term. So let's go back a little bit. So what we have here is that what we're dividing into is x cubed minus 3x squared. And we don't have an x term. We go x squared and then we just go here. So we need to add in that term of 0x. So really all my coefficients are going to be the 1, the -3, a 0, a -8. We're dividing by an x plus 2. That means what I'm going to use for my division out here is the -2. So synthetic division, I'm going to drop the 1. 1 times -2 is -2. Then we add -3 and -2. That gives me -5. Then I go -5 times 2, -2 gives me 10. 0 plus 10 just gives me 10 again. 10 times -2 is -28. -20, sorry. In the end, I'm going to get -28. I was like cutting to the chase there. So this split like this. So this number here is the remainder, as you see right here. This part here, this is your quotient. And remember going backwards, this is a constant, this is x squared. And then if there's another term, x cubed, et cetera, et cetera. So the quotient, we rewrite it with our coefficients, is just going to be x squared minus 5x plus 10. And then, like we said, remainder is this -28. So here we want to graph this polynomial to the right. So we know how a little bit about graphing polynomials because we know if we know where the zeros are, we can make a potential graph. I'll make my little graph a little bigger here. So we see we have a 0 here, 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 and here. So my zeros are at, let me see, 1, 2, 3, 4, 5, 6. One at -6, one at -2, one at 1, 2, 3, and one at 5. So the factors that go with those zeros would have to be x plus 6, x plus 2, x minus 3, and x minus 5. Because remember, you have to switch sign because for this factor to work, I have to set it equal to 0 and solve for x and get that -6 like here, get that -2, get that +3, get that +5. So if I want to construct a polynomial, So we need to find the factors of the polynomial. So we have done that step, found the factors. We're now going to construct the polynomial. That just requires me to multiply those factors. So I just set them up like this. In this question, we don't have to do more than that. Okay, so is it possible to find another polynomial with the given zeros? Yes, because I could just have 2, x plus 6, x plus 2, x minus 3, and x minus 5, and I'd have those same zeros. Is it possible to find another polynomial function with the given zeros in the same graph? This would be a no, because if I had a different graph, like this one has a 2, what would happen is this would actually be an elongated function of this graph. So it wouldn't look exactly the same. So you can still have, you can write another polynomial function that would have the same zeros, doesn't mean it would match the same graph. So as long as we had rational coefficients, we had what we had said were irrational conjugate roots. Our rational roots came in conjugates. And our complex roots or non-real roots come in conjugate pairs. So that meant if I had an a minus b square root of c, that meant that I also would get the root a plus b square root of c. If I had a plus bi as one of my roots, that meant that there was a root that was a minus bi. So they came in conjugate pairs. So my list of roots that they're giving me is that I have 5. I won't have a pair to it because it's not an irrational or not non-real. -4 plus 4i, however, will have another root that goes with this, which will be -5 minus 4i. 2 minus the square root of 5, because this is an irrational root. This will also have another pair to it, which is 2 plus square root of 5. So we want to know, like I said, the fifth degree polynomial, we do need to make sure there are 5 roots. So it will give us 3, but we have to find those other 2 because we know, because of the irrational coefficients, I'm going to have 2 conjugate pairs. So my other zeros would be -5, -4, and 2 plus square root of, or -5, -4i, and 2 plus square root of 5. List of potential zeros. This was the thing about the silly snake put the tail over its head. So remember, head, tail. So my head is the coefficient of 1. That imaginary coefficient, sorry, not imaginary, invisible coefficient. And then that tail would be 26. So my factors that I'm looking for is I'm looking for things that are factors of the tail, which is my 26. So that would be plus or minus 1, plus or minus 2, plus or minus 13, and plus or minus 26. Then I also need factors of the head. So my head is 1, so this one's easy. I have plus or minus 1. So I'm looking for my potential zeros. They're going to be factors of the head over factors of the tail. Or sorry, factors of the tail over factors of the head. So that backwards. because the silly snake puts its tail over its head. So what I'd have is plus or minus 1 over 1, 2 over 1, 13 over 1, and 26 over 1. Which simplifies down to just plus or minus 1, 2, sorry, plus or minus 1, plus or minus 2, plus or minus 13, and plus or minus 26. So this was rational expressions. So with rational expressions, we were interested in finding domain was one of the things. So if we're interested in the domain, we just want to find where the denominator, because we don't want that denominator to be 0, we need to figure out where that is equal to 0. Because wherever the denominator is equal to 0 is where my function is undefined. So x squared plus 2x minus 35 equals 0. So we're going to do factoring for this one. Factors that give me a negative 35 and then add to 2. Okay, yeah, because there'd just be 7 and 5. So if I had negative 7, oops, well, positive. Negative 5 times positive 7 give me 35. Minus 5 plus 7 gives me a positive 2. So my factors would be x minus 5, x plus 7. So what we're doing is really just trying to find zeros that are of the denominator, because those are places that need to be removed. So denominator equals 0. This happens when x is either negative 7 or 5. So those need to be removed from the domain. So my domain is x values, just as long as x is anything but negative 7 or 5. Or another way to write that, remember the number line. The number line is telling me I have everything but negative 7 and 5. Those are like open points. So this is what my domain looks like. I can't have those points. So my domain is from negative infinity up to negative 7. I basically skip over that negative 7, and then between negative 7 and 5, I can have x values. And then I can't have 5 because it makes the denominator 0 and I'm undefined. So I need from 5 to infinity. So vertical asymptotes, these are we're going to be these are located where the denominator is 0, but the numerator is not 0. So we don't really have to worry about the numerator, because if my numerator is 3, it's never going to be 0. So really the only thing I have to worry about is the bottom. So I have x plus 2 times x minus 4 as my denominator. So where that equals 0 means I have to set equal to 0 would be we either x plus 2 equals 0, or when x minus 4 equals 0, which is going to be either x is -2 or x is 4. So the two places I would have vertical asymptotes would be here at +4 and -2. This one, I'm trying to remember what kind of graph this one gives me. But we're going to have asymptotes, those two spots there. So it means it's going to be doing, I think it's this one, but I'm not really sure. But it's something kind of like that. So we see those asymptotes there. So horizontal asymptotes. So our rules for horizontal asymptotes were if the degree on top equals degree on bottom, then we are going to have a horizontal asymptote at y equals a over b, where a and b are the leading or the coefficients of the leading terms. So what that would mean is like this is 1, this is 6. So assuming if the degree in the top and bottom were the same, would be 1 over 6. We have another thing that could happen, degree on top is less than degree on the bottom. In that case, if that happens, then we have a horizontal asymptote, it's just y equals 0. Then our last case was that degree on top is greater than the degree on bottom. And here we have no horizontal asymptote. In this case, the degree is referring to that leading term. So we have that our top is a smaller degree than the bottom. That means I have a horizontal asymptote, but it has to be 0. Okay. So this was it's a composition of functions. So if you remember, if I have f composed with g, that means I have f goes on the outside and g goes on the inside. So we want to know f composed with g and g composed with f. And my functions are x plus 11 and x minus 11. So g is the x minus 11. So we just replace c with that. And f is an x plus 11. So I'm going to leave this open spot because by function notation, whatever is in here goes in this empty spot. So we put that 11 in there. So we have x minus 11 plus 11. This one's a little weird because this doesn't usually happen, but f composed of g is just going to give me x. Now, if I do g composed with f, and like I said, this is just a weird case, g composed with f, then we're going to have g is on the outside, f is on the inside, and f is x plus 11. So then g is just going to be an empty spot minus 11, and what we fill in there is the x plus 1. So we just get left with x again. So usually f composed of g and g composed of f are not equal. This is just a weird case. So in this case, they just both happen to be x. But as you saw in class, they're more complicated things. Our domain, so if we look at my function here, that's just x. My domain is all real numbers. Same thing here, it's just X, so the domain of G composes that is all real numbers again. Now, if we're looking for inverse functions, what we need to do is first determine if the function is one-to-one. So if we graph this function, it's going to be a line that looks like this. So it passes the horizontal line test. So it is the function. Or not function, sorry, it's a one-to-one function. So it passes the horizontal line test. Fx is one-to-one. So yes, it's one-to-one. So because it's one-to-one, that means Fx has an inverse function. When you're looking for your inverse function, what you're going to do is you're going to take your function. And the first thing you want to do is instead of writing Fx, we're going to change that to a y. So remember, Fx just means y. Then we're going to switch places with the x and the y. So x equals 7y minus 6. All right, so technically this is where I do have the inverse. So I want to write it as a function, inverse function notation. So my next step is I'm going to solve for y. So we're going to add 6 to both sides. X plus 6 equals 7y. Then we can divide by 7 to get y by itself. And we have x plus 6 over 7 equals y. So then my very last step is that y equals 7 plus 6. Oh, sorry. Y equals x plus 6 over 7. That is my inverse function. So function notation means I'm just going to write f of -1 of f, because my original function was f, equals x plus 6 over 7. So on Melissa's birthday, this is the exponential growth. She gets a $6,000 CD that earns 5% interest that's compounded quarterly. If the CD matures on her 13th birthday, how much money does she get? So this is the equation. The amount we want is just times P times 1 plus R over N to the T. So P is always the initial amount of money we started with. So her CD starts out at $6,000. R is our interest rate, but it is as a decimal. So because we have the percent, we just divide by 100. 5 divided by 100 is 0.05. That's my rate. N is the number of times we compound in a year. So we compound quarterly. So that's 4. And then T. So she is, how old is she? She's 6 when she gets the CD. It matures, which means that she can cash it out at 13. So the time this is going to take is 7 years. So we have $6,000, 1 plus 0.05 divided by 4. And then we have 4 times 7. So remember, put our parentheses in these places. And what we should end up with is $8,495.95. There's going to be some rounding involved here to get that. So for our logarithm, we're going to convert this logarithm to an exponential equation. So if you remember, we said we have this relationship that if we had a log base A of x equals y, that was the equivalent of saying that a to the y equals x. So we don't have a base listed here. So remember that if we don't have a base, that is what we call the common log. And we know when there's no base there, it's supposed to be just a base 10. So my base is actually 10. That's my a. Then this y, that -3 becomes the exponent, -3. And then what it should equal is 0.001. And then this last one, so we want to express this logarithm as the sum and difference of different logs. So we got log base b of p cubed, q to the 5th, m to the 4th, b to the 8th. So by product rule and quotient rule, I can rewrite this as log base b of p cubed plus log base b of q to the 5th minus log base b of m to the 4th minus log base b of b to the 8th. So our power rule says I'm going to pull these powers out front. So this is 3 log base b of p plus 5 log base b of q minus 4 log base b of m minus 8 log base b of b. And there's one other part here, because remember a log base of this. So if we got log base b of b, we had initially at one point said that is always going to be equal to 1. So this is just 3 log base b of p plus 5 log base b of q minus 4 log base b of m minus 8.